So we have one more presentation. Again, this is a team. I just have the bio for one of the team. So if you, Chuck, you want to introduce yourself when you come up, that'd be perfect. So we're going to start out with Tuyen Lee, who's a postdoctoral research associate in the Department of Civil and Construction and Environmental Engineering at Iowa State University. His research primarily focused on developing new automated methods, computational infrastructure for reducing manual and duplicate efforts in data collection, processing, and analytics for the construction industry. Particularly, his research interest includes building and civil information modeling, or BIM-SIM, digital data exchange, natural language processing, intelligent systems, and human data interaction. Okay, you want to come up?
So I'm Chuck Jaron, and my interests here are in research in digital data exchange. I was a subject matter expert for a scan tour on civil integrated management, and have done some other things in terms of EDC, Everyday Counts 3, 3D modeling, and whatnot. I also lead the construction engineering program at Iowa State University that has 325 undergraduate students and 10 faculty members. So anyhow, with transportation asset management is getting to be more and more of a data-driven business. So that means that we get data from a number of different places in terms of the roadway conditions and ideally in the future, what kind of maintenance is being done on our roads. And that data is stored, and then it has to be analyzed, so we turn it into information so we can actually make some good decisions on it. This is just a look at the number of different databases that we have available, and each state usually has a pavement management system where they've gone through and divided state routes, national routes into interstate highways into segments, and then they analyze the condition of the pavements. But in addition to that, there are a number of national databases that can also be very informative, and each of the states and other transportation authorities contribute to those, and then we want those to be available. So you can see that this gets to be kind of a big data thing fairly quickly. And the data has lots of different attributes, and quite a bit of the data that we're particularly interested in is categorical data. And you get into questions like, in terms of highway user satisfaction or road user satisfaction, the most important thing is how smooth is the road. And for this particular study, we've looked at that as just kind of an example of one of the things that you might be interested in. It's kind of a case study, so it could be expanded into other things, but you might ask the question, okay, we have PCC, Portland cement concrete pavements, we have asphalt pavements, we have old PCC pavements that have gotten rough and they've gotten covered up with asphalt, but then when you go from there, you have subcategories of those. You can have Portland, the concrete pavements that are either jointed or continuously reinforced or other things like that. So you have all these different categories that you're looking at, and if you're trying to find out, where are the rough roads in the state, you've got to go through those categories. Now, the traditional ways that you'd sleuth through all this is you might have some tables which are not very visually intuitive, but from there we can go into like our stacked bar charts, and there it gets to be a little bit more intuitive, but it doesn't show you the hierarchical relationships because like with concrete pavements, there can be different kinds of concrete pavements, you know, a subcategory under that hierarchy, and you want to be able to keep track of that, and you lose that. You can go into a tree map, which, you know, starts to address those kinds of things. But what we're interested in here in this study is to come up with something that's a little bit more intuitive, like this map on the left. And you're looking at population here, and it becomes pretty obvious that China and India, that have a big red dot that's bigger than the geographical land area, are very highly populated areas. Whereas you look at Canada, the Russian Federation, and Australia that have very tiny dots compared to the land area, well, that's a fairly low population density. So Tuyen here has done a lot of very detailed work to come up with something that's fairly intuitively obvious, and we're quite proud of. So Tuyen, I'll let you take over from here.
Thank you, Dr. Jaran, for a great introduction for the study. So as Dr. Jaran has mentioned, for transportation asset data, the categorical data is the most common types of data attributes. And when we evaluate the performance of an asset, basically we have to make a comparison between different categories. So we need a effective method that can help us quickly make the comparison between categories and help us easily capture a summary of the data. So to fulfill that need, our study research group has developed an automated method that can support you in visualizing transportation asset data. And we introduced the new concept of heat trees as a new way to represent transportation asset data, especially for categorical data. And we designed the system based on two different criteria. First, the system must be able to identify what data to be visualized. So in the current practices, as a user, you have to have considerable programming skill or expertise to be able to use visualization tools. And you have to specify what data to be visualized. So the development of this function in our system would automate this process. And as a result, it can help us save a lot of time. And the second design criteria is to maintain the hierarchical structure or the tree structure for the categorical data, which is not supported yet in the current data visualization methods. So this is the system architecture. The system has three components: the ontology, data taxonomy, and the heat tree generator. Domain ontology and data taxonomy are critical resources that are supporting the generation of heat trees. So the first components of the system is a highway transportation and ontology. So what is the ontology? The highway transportation ontology is basically a machine-readable representation of the domain knowledge. It presents the definition of concepts in such a way that computer system can understand the semantics, the meaning of the data attributes. And data ontology is a graphical structure which is composed of nodes and links. The nodes represents the domain concepts, and links represents the relationship between concepts. So in this study, the ontology developed involves 6 different concepts, including climate, condition, maintenance, administration, traffic, and design features. And those concepts are related to each other through 2 types of relationships, effects relationship and has relationship. And the purpose of developing this ontology is to enable computer systems to understand the semantics of domain data attributes. So this table showing the attributes for different concepts in the ontology. So for example, here we have the condition concepts. It has 5 different attributes, IRI, PSR, routine, faulting, and cracking. So those data attributes allow computer system to recognize a particular concept and helps computer system to distinguish this concept with another concept. And the second component of the system is a set of data taxonomies. So what is data taxonomy? Data taxonomy is basically the classification hierarchies for a particular data attribute. So this table here showing the data taxonomy for the data surface material type. So the roadway surface can be classified using a 3-level hierarchy. The first level involves unpaved pavement, flexible, rigid, composite. And the second level and the third level involves subcategories of those items in the higher level. So this data taxonomy will be used for generating the heat trees for pavement transportation information. The last component of the system is a heat tree generation algorithm. So the algorithm consists of 3 steps. Step 1 is to identify what are the related data attributes to be visualized. And step 2 is to construct a hierarchical tree for the categorical data. And step 3 is to generate heat trees for the data. And what is the input we need from the end user? So the end user has to provide the input information, including a data set and a base data attributes. A base data attribute is basically the hierarchical, a categorical data that you are interested in. Let's say it is the surface material data. In the first step, the algorithm will identify what data to be visualized using the ontology. And in the second step, the algorithm will develop the hierarchical tree for the surface material type based on the data taxonomy resource. And in the last step, the algorithm will develop heat trees by mapping the values of the data with the hierarchical tree. So by the end of this phase, you will have a number of heat trees, and each heat tree represents the data for a particular related data attributes found in step 1. So this figure illustrates the heat trees for the basement condition over the surface hierarchy. So these figures provides us 3 key information. First, by looking at the tree structure, we can easily figure out how roadway surfaces are classified. For example, the roadway surface system for Delaware can be divided into flexible, composite, rigid, unpaved, and others. And for the flexible pavement, we can further divide it into bituminous and flexible overlay. And second, by looking at the size of the 3 elements, we can figure out the distribution of roadway over a particular data attributes. So as you can see here, the composite pavement seem to be the most popular materials in Delaware. And lastly, if you look at the color scheme, you can easily see the level of performance for different categories. So as you can see here, flexible seem to not perform well in comparison to composite and rigid. But if you break the flexible pavement into bituminous and overlay, flexible overlay, you can see that flexible overlay, even though it is categorized as flexible, but is performing very well compared to others. So basically, based on those information, you can identify what is the best alternative for a particular area. So in summary, what are the advantages of using heat trees to represent transportation asset information? So first, heat trees can present multiple variables on the same plot. So you don't have to create different plots for different information. And second, it can present the categorical data in a tree format. So it is much easier for you to figure out the classification system. And finally, by using the size and the colors of the three elements to visualize information, it is easier for us to make a comparison between different categories. And still, our research still have some opportunity areas for further development. First, future study is needed to develop an open source R package that the end user can easily use for visualizing transportation asset data. And second, we also need to develop another module that can support generation of temporal histories that can show the changing of data over a period of time. And lastly, we need to expand the ontology to other construction sectors, transportation sector like bridges and tunnels, and others minor assets like culverts, guardrail, or size. So that concluded my presentation today. Now I will be open to any comments and questions.